Hello everyone, this is Cider88 back with part 2 of my how to use Pymol video. In this video we'll be talking about displaying individual amino acid residues, using the measuring tool and finding polar contacts, and I'll touch on in silico mutagenesis in the end. These techniques are basic, so it will be a good idea for you to familiarize yourself with them. Okay, we'll be using the same structure that we modified from part 1 of the video. If you want to be up to speed with what's going on, I recommend checking out part 1 first. However, it's not absolutely necessary because these techniques can be applied to any protein structure. Right, we're going to be focusing on the antibody and Ebola virus glycoprotein interface. Now, what am I talking about is this. This is a overall schematic of what we're going to be looking at. The Ebola virus glycoprotein is made out of GP1 and GP2 domains, and here we have the antibody, and it's going to be shown as a FAB. We're going to be looking at the interface region shown by the red star, and that's definitely what's most interesting about this structure. And we're going to go ahead and close out of this, and we're going to look at this interface. We're going to go ahead and jump right into the program. This is the structure from part 1 of the video. Alright, just to review real quick, the blue and red shows the heavy and light chains of the antibody, the green shows the GP1 domain, and the orange shows the GP2 domain of the Ebola virus glycoprotein. Okay, so let's go ahead and, this is in a trimer because that's what the protein is like on the virus. Alright, so let's now focus on the interface. Specifically, we're going to be looking at the arginine 98 from the antibody and the glutamine 50A and proline 509 from the GP2 domain. Now, what am I talking about? Okay, let's go ahead and look for the residue number 98 on the antibody. Let's see, 96, 97, 98. Here we go. After I selected it, you see here on the image it is selected, but we really can't see what it is. It's just these purple dots. So what we can do is go to the show, sticks, and then color by element, and now we can definitely see it in a much clearer way. What else do we need? We need 508 and 509. Okay, so for the GP2 subunit, we're going to scroll all the way down. I know for sure is this one, J. Chain J, we're going to go ahead and select 508, 506, 507, 508, okay, and then 509. Okay, great. We're going to go ahead and show sticks, and we're going to color the same thing we did last time by element. Okay, great. Now we see these 3 residues. Let's go ahead and rotate it in a way that we can get a clearer sense of what's going on. Alright, let me zoom in. Okay. Alright, great. I think this is pretty good. So here we see arginine 98 from the antibody, and here we see proline 509 and glutamine 508 from the glycoprotein, GP2 domain specifically. Okay, now what we're going to do is, so basically now I've shown you how to display individual residues. Next, we're going to learn how to use the measuring tool. We're going to go ahead and go to the menu. I'm going to go to wizard and then measurement. Okay, we're going to go ahead and click here on the oxygen and to the nitrogen, oxygen, nitrogen. Okay, and then done. Now, so from this oxygen to this nitrogen, it is at an 2.8 angstroms. From here to here, the nitrogen to this other oxygen is at 3.4 angstroms. Now, why do we care about these angstroms and measurements and such? Well, the reason why I selected these residues in the first place is because you see these oxygens are dipoles, right? So they have a negative charge. However, this side chain here, the arginine, is a nitrogen, and this is most likely an NH3, since this is a basic amino acid residue, which has a very high pKa value. So at physiological pH, this is most likely charged. It's a proton acceptor. So if this is positive and these are negative, it is most likely these are forming very favorable interactions. Hence, the antibody to antigen uh, binding is possible. Okay, so, whoops, sorry about that. So, how do we prove or basically confirm in a way that these are favorable interactions? Well, first of all, we can look at the measurements. They're 2.8, 3.4 angstroms. These are very, very reasonable values. Another way to do this is by showing polar contacts. Now, what we're going to do is go ahead and hide these measurements. Next, we're going to go ahead and click on the arginine itself. We're going to go to A. We're going to find polar contacts and to any atoms, basically, is what I like to use. Here we go. Once we did this, the program automatically shows us all the potential favorable interactions with this residue to the surrounding residues. And two of these interactions are exactly what we just measured out: the two oxygens to this nitrogen, the negative environment to the positive environment. And there's some other interactions as well here and here, but we don't have to really talk about those because this is just an example. And it's just showing basically there are many favorable interactions, and definitely the important ones are the ones with the antibody to the antigen. Okay, so after that, we'll go ahead and hide this. Now, let's say you're doing some kind of antibody engineering. You want to really kind of look at this area and this residue specifically. So you've done all this and you really want to say, okay, well, I think this residue, arginine 98, is extremely important for this antibody in order to recognize the Ebola virus glycoprotein. And you want to start mutagenizing it. Well, you can actually start mutagenizing this residue in Pymol itself. This process is called in silico mutagenesis. In silico just basically means using the computer to do some kind of a simulation. Okay, one way, what we want to do is basically abolish this favorable interaction between this arginine side chain and these oxygens on the backbone of these residues, right? If we abolish these favorable interactions, and if we can mutate this to a residue that won't have this contact anymore, and then no longer this antibody can bind to this antigen, then basically we have proven that this residue is very important for these for this antibody recognition of the antigen. Of course, there's other interactions going around between these two around this interface in general. I mean, that's definitely true. But for example, you just really want to focus on this residue, and it looks very promising. Okay, so what we can do is mutate this residue, for example, into a acidic amino acid. Acidic amino acid will have a negative charge, the same charge as these oxygens. In that case, we'll actually abolish this favorable interaction for a non-favorable interaction. So because opposites attracts, but if you have the same charge or the same type of environment, you're going to have repulsion instead. And that could definitely hinder the antibody recognition to the antigen. So what we can do is go to the menu again. We're going to select wizard, this time mutagenesis. Alright. Next, oops, sorry about that. Next, we're going to pick a residue. We're going to pick this arginine. Okay, and it zooms in a lot. Alright, I know this looks very messy, but let's go ahead and I'll walk you through this. So if we look at the mutagenesis panel, we want to assess no mutation. So we're going to go ahead and select mutation. We're going to select glutamic acid, which is an acidic residue. We're going to click it. Okay. Now, if you look down here, it says state 1 out of 19. So this gets pretty complicated because if you can imagine the side chain of an amino acid, the more carbons it has, right? Alpha, beta, gamma, delta, etc. The more torsion angles it can adapt to, and this is based on the surrounding residues and other charges in the molecule, and a lot of other, basically a lot of three-dimensional modeling based on the other residues in this environment. I don't particularly want to get into torsion angles and 3D space occupancy at this point. So that's way beyond the scope of this video. But what I do want to point out, the program does allow you to select different rotameric states. So if we can go ahead and click through these, you can see the side chains adapting to different conformations in the three-dimensional space. Okay. Now what's interesting is that if you go back to the first one, the default one, it says 19.7%. 19.7%. If you go down to the next one, it says 9. Then 8.7, then 8.2, 7.7, 7, etc. Okay, so basically what this is showing is that the default residue that you do mutagenesis on, it will always show you the one that's of most likelihood to adapt the conformation. Everything else as you click through, it's going to get lower and lower and lower and lower in the percentage of likelihood. So what I like to do is just keep it as the basic percentage, the highest, the default, and that's usually pretty good. So we like what we see, and we're going to accept this, and we're going just to click apply, and this is going to take a couple of seconds for the program to render your request. Don't click anything else at this point; it might crash the program. So we're just going to go ahead and wait this out. And we're still waiting. Hopefully this works. Okay, there we go. Perfect. So now we have the arginine has been mutated into the glutamic acid. So we're going to click done for the mutagenesis, and let's take a look at our structure now. Okay, so here's our new residue, and let's see if it still forms any favorable interactions with this area, or has any at all. Let's see, did we abolish our favorable interactions? We're going to go to A. We're going to go to find polar contacts again to any atoms. Okay, and there we go. We don't see the yellow dashed lines anymore from this position to these oxygens anymore, because this itself now has become an oxygen. So there are no more favorable interactions, and indeed this oxygen to this nitrogen over here is probably just too far away. I mean, although they are of opposite charges, it's probably way too far away for any interactions to occur. And indeed, the only interactions we see is just in the backbone, which we already saw anyway. So by mutating this arginine into a glutamic acid, we can safely say, at least based on Pymol, that we are abolishing favorable interactions, and this can lead to the antibody not recognizing the glycoprotein anymore, or perhaps has much lower affinity. And that's pretty it. Of course, this is only a predictive software, and there are many other interactions to take in consideration. But if you want to mutate these residues, for example, for a presentation, or kind of explain to other people what you're trying to do, it's a really great visual tool. Of course, you want to do the actual experiment. That's the only way to find out whether or not this mutation is relevant or not. But as a visual tool to show other people what you're going to do, or planning out experiments, is definitely very helpful, just to kind of see everything in a three-dimensional space. Okay, well, this is basically the conclusion of part 2 of my Pymol video, and I would just like to thank everyone for watching and listening. And if you like what you saw, please subscribe to me and subscribe to me and like the video. Thank you guys so much, and this is Scyther88 signing off. Until next time.